Hello everyone and welcome to another episode of VM hacking. Since the last video, I've worked a little bit on the garbage collector, or rather, actually a lot on the garbage collector, and have gotten it to the point where it mostly works. At least I haven't seen any garbage collection related bugs in a while. But the problem was that performance was suffering a lot. So the basic Advent of Code 2020 Day 1 example I was trying was taking about a minute to execute the part 1. Through various things, one of which actually improved performance by 97% because I stopped copying things, I was able to bring that down to about the second and a half on release fast mode, and I can just show you that. Let me just do that 1 second. That again. There you go. And yeah, before this would take about a minute, now it takes about a second or so. Of course, in debug mode, it's kind of slower, but it's debug mode. So what I want to do today is look at another performance optimization that we could do here. Now, uh, in our self code, or rather self virtual machine, we have these things called activation. So what activations are? They are a record of the current executing method or block, and they will hold an activation object value that you can see right here. And what happens is that when you activate a method or a block by sending it a message, like sending the object a message with that method or block's message name, an activation will be created with an associated activation object. You could think of the activation object as your like function scope in other languages. But the thing with the activation objects is that when we create an activation object, because the blocks need to hold references to these activation objects. So when we, for example, want to non-local return, which is a feature in Self, where you can return from a block, and it returns for every single block that's currently on the stack and exits from the top nearest method. So, or rather, the method that the block was defined in, right? So what we want to do is hold references to the activation which we should return from. But the problem here is that we cannot do that unless we know exactly where the activation is to be able to match it. And because of that, we can't use a simple array and in place initialize the activation objects in the array, because then if we add new items to the array, let's say it's like a Zig's std auto array list, I think that was the name, or std array list. Yeah, I confuse those sometimes. So let's say you have a std array list and you have 10 activation objects in it, or rather 10 activations, and activation objects are a different thing. And if you add an 11th one, you have a chance of the object resizing, the array list object resizing its internal storage, and that resizing operation might move the inline initialized activation object somewhere else. Now, all of a sudden, the activation object the block was pointing to is now gone. So until now, what we have done is keep these activations on heap memory that's outside the object heap. That's like the operating system heap that's provided to us. We keep them there. But the problem is that creating and destroying these activation objects takes a lot of time. In my profiles, it took about like 20% or so of the time it takes to execute a single method. And if you add those up, they add up. So what I want to work on today is finding a way to have these activations without having them allocate on the heap, and at the same time uh, not have them move during runtime. And when I did a calculation, so let's say that because we could just learn how big these things are just by doing a compile log right here. And if we do that, this will print the size of the object. So in release mode, there are 120 bytes, and in debug mode, there are still 120 bytes. I could have sworn I saw like 136, but I might be mistaken. Maybe that was something else. I'm not sure. But so there are 120 bytes, and if you do a little calculation here, what we'll come up with is that our current maximum stack size, beyond that we say like, okay, you can't call any more functions. So that's currently 2048, and that's defined right here, maximum stack depth. And if I multiply that, that's 245 kilobytes. Kind of irrelevant in the grand scheme of things. And even if we double this, we would only be using 500 kilobytes. So what I'm proposing is that when we first start the VM and we're in execute script, which is this function right here, this execute script function where we initialize the activation stack, instead of initializing this array list, which can dynamically change size at runtime, I propose that we could instead simply have a single statically sized array, or rather, like statically allocated array that sits on the heap and never changes size during the program execution. And for that, I think what I'll start with is moving this maximum stack depth here out onto here. So I'm going to keep it as 2048 for now. Let's make this a pop const, because what we need is, okay, root interpreter, and then const, what is that, maximum stack depth. Okay. So now that we have that here, and the message interpreter parts can accept this, let's actually use that, and let's actually take advantage of that. And instead of doing this, what we can do is activation stack try allocator alloc, and we're going to allocate activation objects, and we're going to create maximum stack depth of those. Okay, so now that we've done this, instead of doing that, what we're going to do is, oh yeah, let's keep these defers, but instead of that, we're going to say allocator free activation stack, and when we are deferring, we're going to say for activation stack, instead of items, because we're going to be storing the stack directly instead of an array list, and we go through each one of them, and instead of destroy, we're going to say dinit. So a convention that I've come to use in self code, or rather in Zig code, is that we have create and destroy paired to allocate an object on the heap and initialize it, and I'm using the terms init and dinit in place of the constructor and destructor in languages like C++. So that's just a convention that I've seen others use, and I've decided to use it as well. So that would become, instead of destroy, it would become dinit. So, okay, we set the activation stack on the heap. So we need to go to the heap, and instead of having an array list here, we need to have a pointer to a slice of activations, an optional pointer to a slice of activations, and we say activation stack is null. We also have a set activation stack, and that will be taking a slice of activation, right? Okay, and then activation. Look at that. Okay, self activation stack activation. Okay, so instead of that, we have that now, and instead of this, a pointer to activation, we have simply the activation slice itself. And yeah, okay. So let's look at more instances of the activation stack. Okay, instead of a pointer to activation, we have these. Yes. And activation stack. I guess it doesn't hurt to keep it const. In fact, we could simply keep it const everywhere. So, Actually, now that I think about it, there's really no point to having a pointer to a slice because a slice in Zig is just a pointer plus a length. So there really is no point to having a pointer to a slice itself. So let's keep it like that, and this slice is owned by interpreter code. Let's say this slice is the stack of activations owned by an interpreter code. Oh yeah, something important that I haven't considered is that how do we... Oh yeah. Oops, I haven't thought about this. A problem that's going to arise from this is the fact that now we have a statically sized chunk of allocator, or rather activation memory, but we don't know how many items are in it. So I believe what we can do there, because ArrayList internally does some unsafe stuff where it actually manipulates the length of the items slice itself, but that code has been pre-battle tested, and I'm not sure if I want to do that. So what I can do, I think, is well, actually, okay. So what I was thinking was that we could have like an activation stack struct, which holds the current number of items, but then I need to hold a pointer to that. So let's say I have an activation stack here, and when I'm holding this activation stack, we can just place that in activation.zig. Right. Pop activation stack. Oops. Struct. Stack. Activation. And then depth, we could say, is usize. Okay, pop activation stack struct. Okay. And we're going to hold a we're gonna have activation and then const activation stack. I guess we could just place it here. Activation stack. Okay. And we hold an optional pointer to, okay, it's not a slice anymore. The stack of activations owned by interpreter code. Okay, so let's start with that. And instead of this activation stack, let's say, yeah, let's just do that. And let's have an initializer for these, so I'm allowed to pass like a dot, I'm allowed to do the syntax for here. Oh, it's in pointer to an activation stack. Oh, that's annoying. Am I allowed to do this? I mean, we can try. I remember something related to this actually working. I'm gonna try that. Uh, okay, and then depth would be 0. Okay. And actually touching that is illegal. So what we should do is we should have a const footer to this activation stack right here. So footer const activation stack. And we pass that stack to allocate an object segment. And we do the same thing with allocate and microwave segment. So let's do that. Okay. Oops. Stick hole in there. There we go. Set activation stack is now going to take a pointer to an activation stack. And we do allow it to be nullable because we want to disable the activation stack after we've exited the script part. So, mark address, yeah, okay. Nothing. Oh, I missed this here. Okay, and then I simply, okay. I believe that is sufficient. Right, this won't work anymore. Let's replace that with a dot. Right, so collect garbage internal. I can just pass that through, no problem. For activation stack, 0 activation stack depth. So that would be how many items are in it. Right, and then that would just simply hold reference to the activation object, I think. I'm pretty sure the optimizer then can figure this out. So I'm not gonna like add a pointer to this or anything. Okay. So activation, or maybe not, it might not be able to do that because we do modify it. Okay. We mutate the objects that are within the activation stack. So let's add a pointer to that just in case. And I think the rest is simply changing some definitions. There we go. I think that was the last, or rather second last. Okay, and last one, I think. Oops. There we go. These tests are broken. I will eventually get to them, but yeah, they are useful tests. I just haven't used that functionality in a while. I've been working on with actual code instead of having these like unit tests. But I will definitely get back to those probably after this video, because after this video, with the performance work and whatnot, I pretty much accomplished what I wanted with the garbage collector and whatnot. So I'm probably going to get to adding tests, adding standard library features, and those kinds of things. So that's my short-term plan, let's say. And let's see now. So we made that change. Now, in the interpreter code, what we need to do is set the activation stack. Right. So we're gonna have a activation stack. That's mutable. Activation stack. And let's have a war activation slice. And let's have that as the thing. Or rather, why am I doing this code right here myself when I can just do something like init defend init, take an allocator here and return an activation stack. Max depth equals or rather usize. Right, this will be ensured because the stack item member will contain the maximum length by its slice length. So this will be already encoded. We don't need to add it as a new member. Okay, so in init we say const slice or const stack. Let's be consistent. Right, allocator alloc self, and we're gonna allocate max depth items. And I don't think there's anything tryable here after that, so let's just return activation stack. Stack equals stack, and depth can be default initialized. Okay. Okay, now, and we're also gonna have a deinit self activation stack and allocator type, and we just do allocator free stack, or rather self stack. Okay. So let's clean up these mess. Activation stack init. And maximum stack depth will be the thing here. Now it's going to say, what the hell is an activation stack? Let's add it in. Okay. Now, the interpreted context actually has to contain that as well. So let's say pointer to an activation stack. Pushed objects must be pushed with the assumption that one ref is borrowed by this stack. We don't. Do we still use ref counting in activation objects? Ref? No, we don't. The activation objects themselves are not ref counted, so there we go. Yeah. Okay, so activation stack, sure. And right, it will have an initial thing of 0. We go through the activation stack. And that would say defer activation stack, the init, allocator. Let's also pass the allocator here. And we go through the activation stack. That's stack 0. Get slice. Yeah. Or let's say get stack. Above and get stack self. And let's return a slice activation here. And then we simply return stack 0 to self depth, self stack. And that's going to give us the portion of the stack that's currently being used. So, okay. And we simply deinit that. Okay. Or we might want to, yeah. We want to do that because deinit here And we're going to get rid of these in a second. Or you know what, let's just get rid of them as they don't do anything interesting. So let's pub these. Okay. So this needs to happen, let's say in place for this, because we can't initialize this and then copy the value inside the activation stack. We need to initialize it outside because what happens is that we initialize a weak block here. Weak blocks are basically weak pointers, and we need to know the exact address of this activation when we are like creating the activation object. And we cannot do that if we like if we copy the element out, there is no way to notify this weak block that, hey, your address has changed, you live here now. At least in Zig there is not. Maybe in the future there will be something like that, but at the moment we need to initialize it in place, which is kind of messy, but yeah, we can live with that. Okay, so we track the lobby, we get the activation stack, yes. Okay. And I believe rest of this code can be mostly untouched because none of them really do anything with the activation stack. Oh yeah, that part of code, I forget. We need to do that. Copy that once more. And this object will do something with that as well. Or rather, oh yeah, it doesn't, never mind. Okay. And does anybody else... Okay, context activation stack. Okay, we need to get the last item stack. Contact, get activation stack. Depth, -1. Okay. So this would be what we do, and... Okay, anything else? And when we're executing a non-local return, we need to do stack. Instead of items laying, we do depth. Okay. And I believe that's all the changes we need to do in this part. So let's look at the message interpreter because that does a lot more seedy things with... So for example, the block message part, what we need to do here is... Okay, so block object, we get the block object. So what happens here is that in self, you cannot execute blocks after they have left, like they have been returned outside the... They have been returned outside the activation that they belong to. For example, let's say, let's create an example for this. So let's just create something scratch. Let's say that I have a thing here, and let me include... And let's say, let's have a variable v that get block, and then I do v value, let's say. Let me not forget the slot things again. And get block would be return. Or rather, the return is the last expression. So, hello world, print line, let's say. Okay. Let's say that we do this. Now, let's run it. And what you'll find is that attempted to execute a block after its enclosing method has returned. Use objects for closures. So the logic behind this is that we don't want to have the kind of lexical scoping, let's say, or rather closing or that really complicates these things. You already have something called an object, and it can just as well receive a value thing here. So let's change this code to instead do the following. Let's say value, value, hello world, print line. And if we do this, first of all, we don't need to close on any values. And second of all, we can just call it however we want. So blocks are mainly used in this context to have something you can pass the other objects in order to, for example, iterate, do control flow, and things like that. It's not meant to be a closure. If you want a closure, you should create an object which could have the, let's say, uh, yeah, okay. So I don't want it to go too much of a tangent on this, but if you want to ensure that it has a specific contract, you could create an object which has default methods and then override them in an object which parents that object. So you have an object foo. Object foo has like a value method that says error not implemented, and you could have an object which says parent foo interface, let's say, and then you have a value that overrides that, and then you just call that. You could say it's duck typing, but I think it works fine for what it's supposed to do. So let's move that out of the way. So what this does here is it looks at the block map and it gets the parent activation, which is the activation that this block belongs to. And if that activation is gone, then it says, no, I cannot do anything here. You have returned me from where I belonged, and I cannot execute because all the variables that I could potentially execute might have been deleted, might have been garbage collected, anything could have happened to them, so I cannot continue here. So what we need to do here is, okay, we do this in cast I size. Yeah, because we could we want to do a backwards iteration. So blocks that belong to closer stack frames to the top of the stack will be faster to check for. So that's why we do this thing here. So let's do depth. And okay. Stack. Cast U size I. Yeah, it's Zig is Zig is very strict about these incast things, and that can be both good or bad. Good in the sense that it actually forces you to think about, okay, am I truncating value here accidentally? Unlike in C, where you would just do an implicit cast here. But it also can cause these kinds of churn. It depends. It's really situational, I'd say. But it does make you think, which is a good thing. Okay, so the rest of the code is okay, and depth. Let's add a fix me here. Instead of doing this check manually, let's add. Huh. Okay, let's keep it this way, and I'm not gonna add a fix me either. Let's keep it this way for now. Let's see. Wait, do I not have the latest changes here? Well, excuse me. I think I did not pull in the latest changes here because I did have a bunch of changes, and it would be a mistake to not make my changes on top of that. So I'll be right back. Right, we're back. Sorry about that. I just had to pull in the latest changes, and the latest changes were things that are related to uh, not copying more things across the virtual machine during runtime, which does slightly improve times. So let us say that we have, okay, where were we last time? Yeah, okay, so we create the block message name and we say, okay, so activate block currently creates a runtime activation object. What we need to do here is, instead of doing this ourselves, or rather, let's instead of doing this in the slots object, or because this is convenient, because I want to keep it contained to the object itself, but at the same time, I don't want to like heap allocate this. So I think what I can do here is make this an out parameter, out activation, say activation. And this out parameter will be initialized like so. And yeah, I believe that will work just fine. Yes, and let's do the same thing for activate method while we are at it. Activation. Okay. And we're gonna say try activation init in place. Okay, so this will be initializing the object. Okay, let me think about that for a moment. Is there anything that we might mess up here? I think this is fine. Does init in place return? Yeah, okay, try this. Okay, so let's go back to here. And now we need to pass this the activation. Instead of doing that, we need to do yes. And for block activation, we don't need to get this out here because we don't allocate that anymore. So what we need to do is const new activation, get new activation, context activation stack, get activation for init. Okay, context activation stack, get activation, get new activation slot, let's say. And what this will do is, where was that? Oh yeah. Find get new activation slot, self activation. Why did I say activation block? Stack. Yeah. An activation. And what this will do is more activation equals note will trigger a crash if So stack depth was exceeded, let's say. And activation self stack self depth, and self depth equals 1. And let's return that activation that we just got. Okay. So new activation, this will give us a new activation slot, which we will initialize in place. Right, so we don't need to do this anymore. And there really is no reason that we need to do that outside either. The reason I'm having this in a block is because if I don't have this in a block, then let's say that this code fails in some other place and we are unwinding the stack. These error defers will unref the script object while it's still being used, because the activate block thing stores the ref of the script object, like the pointer to the script object, inside the object heap as like an encoded integer. And if we run all our finalizers, as part of the finalization procedure, that ref will be unreffed. So if we do a err defer here, what happens is that we run this err defer, and then we also run the finalization thing, which also unrefs it. So that will be causing a mismatch, like it will cause a double unref, let's say. So let's not do that. And in here, we have a new activation. Okay. Block object, activate block. Okay, did execute normally or did not local return. Up the activation. We're not doing this. Or let's just say pop activation. Why not? And instead of that, just because this will be technically still valid because we're not running multiple, like this is thread unsafe, but we're not running any other thread, and any thread would have its own activation stack anyway. So this is fun. And I think what we will do is activation. And yeah, I'm just comparing the addresses here, which could be wrong. Note, this isn't perfect, but should be a good enough heuristic that something is seriously wrong if it fails. Yeah. Okay. So we create a new activation, that's fine. And I believe that, oh yeah, it does say block activation. So let's bring that back. There you go. Great. And break block activation. That will give us the block activation as we wish. And right. And that was the last time we use it. Okay. And I believe that is block messages done. Now, the second thing we will do is right here, stack, or rather depth, and that's the maximum stack size. And the method activation, we are going to do the exact same thing as here. We're going to get a new activation slot, and we're going to pass a new activation right here. We're not going to append anything, but we are going to do that. There we go. And I believe that is pretty much it. Same deal as in execute block message. There are parts which are common between block and method activations. They're basically like they're very similar things, but they do have different parts that shouldn't be included. And I feel like conflating those two pieces of code together might cause more problems than we initially want. So I'm keeping them separate for the time being. So that's why we have to repeat that twice, let's say. Now, let's try compiling that. Okay, so we did a mistake in syntax, apparently. Oh, yeah. We dropped that. Don't need to do that. And it says activate. Oh, yeah. Because you're not. In this context, the activation symbol is not defined. And we also say activation in a bunch of places. Right here. There we go. And we say no member name. Interpreter 104. Oh yeah. When we are executing the root script object, we want to make sure that every single time, every single statement we execute, we have exited all the activation like all the activations already. So that's just a sanity check more than anything. Okay. More errors. 117. What did I miss? Print trace from activation stack. Get slice. And I didn't run ZigFMT here. I'll probably have to fix this at some point. I don't remember how I fixed this on my other Emacs setup, but yeah. Okay, incompatible types, runtime activation. Let's see. 390. What is the parent activation? Oh yeah. Can't do that because that would be causing a copy. That's kind of messy. And slots.zig 544. Now activation init in place. Expected utility ref counted. Ref putter. Got language location range. Okay, so what am I doing wrong here? So we have a self allocator heap, activation object, creator message, range, script. Oh, I think I messed that up. Or maybe it was always messed up and hidden behind that. Okay. No member named get slice. Get slice. Was that get stack instead? Probably was. Yeah, it was. Okay. And expected type runtime activation putters instead received. For that, we need to go here. Let's do this to our. Since this is const, it should be fine. Right, and we're slicing it up however we want, so that's fine. And in another place, we're doing the same thing. Message interpreter says something that should do. Oh yeah. Since there, I don't think remove that was the right choice. What did the init require again? Hold on, I'm forgetful. It did not require anything. Okay. So the other destroy should become a D in it. Incompatible types, runtime activation, and a pointer. Okay, so why does it say that? Uh-huh. Because we have raw activation objects there now. Expected type, runtime object slots. Oh yeah. I believe that is a mistake in the slots code. Yes. We need to do a runtime activation because we do have something called activation objects instead of simple activations. Okay, that did build. Now let's see if it is able to run without crashing. Oh, it did. It did nothing. What? So, oh, because we're doing zig build. The zig build run, and it does seem to work. Is it? Yep, it works. Cool. And as a final thing, Hyperfine is installed. That's great. Now, let's build. And I am going to commit this in just a second. So let's do a release build of this, and let's see whether this has improved our performance, because I have theorized that it would improve our performance, but of course can't know without actually trying it. And let's see how fast this runs now. Oh, oops. That replaces the object there. Big out and self, AOC 2021, solid self. Seems similar. So the previous time was about 1.43 seconds. I will test that after I've done the commit. Let's try Hyperfine. It actually says it's pessimized a little bit, but it could be because I'm currently recording, and it does have a toll on the CPU. So what we should do is go here and yes. And let's have all these changes added in. And let's commit them. Runtime. Use in place activation objects instead of keep allocating. This allows us to avoid many allocation and deallocations during method and block message execution. Okay, and let's check out the previous commit, and let's build that in our, let's say, okay, let's build the previous commit as the release fast build and compare if it improved anything. Did it pessimize anything? We don't know yet. Okay, and let's do a hyperfine of the previous commit. Okay, so let's see what hyperfine tells us here. And it says that the previous commit uses about 1.9 seconds. If I go to master now and rebuild, and then test it, and I believe the number was somewhere around 1.5 seconds. So if that's true, we made about 25% of performance improvement, which is great. So let's just double check and let's go. Yeah, we made about 25% of performance improvements. Of course, it could vary a lot because I'm CPU recording in OBS, so it could definitely vary based on time to time. But it seems like, and let's confirm this, take the means and divide them up. Whoops. Except 2. That is a 21% improvement. Let's just add that. This improves performance by 21% on the Avalanche of Code 2020 day 1 part 1. Part 1 code. I have not executed part 2, and I will tell you why in a second. Because if I execute part 2, you will notice something, which is kind of unfortunate. Let's not do that. When we do this, it will fail after a while, and it says to do expanding a space which doesn't have a tenure or scavenge target. There is something that I have yet to figure out, and that is the fact that for some reason, there is way too much data that's being stored, and currently in the old space we only have 16 megabytes of data, or rather 16 megabytes of heap space, and I have not implemented the expanding of that space yet. So there are two things to consider here, and those two things are, first of all, why am I storing so much data in the old space? Like, what am I referencing? Is there something superfluous that I'm referencing? And the second thing is I need to be able to expand this heap so that I am able to run programs which require larger amounts of memory than 16 megabytes. Because, of course, that's a lot of programs. So that will be for the future. And for the time being, if you reach this part, hello and thank you. And I will see you next time. Bye bye.